So it's my honor to introduce our first two keynote speakers today. Mr. Atsushi Inoue is Vice President and Technology Executive in the Memory Division of KIOXIA Corporation. With over 30 years of experience in the flash memory industry, he plays a crucial role in product planning, technical marketing, and customer support for the latest 3D flash memory, BICS Flash. Mr. Inoue graduated from the Department of Materials Science and Engineering, Faculty of Science and Engineering, Waseda University in 1993. In the same year, he joined Toshiba. In 1999, he moved to Toshiba America Electronic Components, where he supported the initial growth of NAND technology. Further on, he has worked with many versions of TLC and QLC technologies and planning NAND products for the enterprise and data center markets. Recently, he served as Senior Director in the Memory Technical Marketing Managing Department before assuming his current position. Mr. Inoue is currently based in the KIOXIA Corporation headquarters in Tamachi, Tokyo, Japan. Our second speaker is Mr. Ichhaporia. He holds the position of Senior Vice President and General Manager of the SSD Business Unit at KIOXIA America Incorporated. In this role, he is responsible for the company's marketing, business management, product planning, and engineering teams, overseeing the SSD product portfolio aimed at cloud, data center, enterprise, and client computing marketing segments. Neville has over 20 years of extensive industry experience across a variety of responsibilities and disciplines, including product management, strategic marketing, new product development, hardware engineering, and R&D. Mr. Ichhaporia holds an MBA from the Santa Clara University Levy School of Business, an MS in Electrical Engineering and VLSI Design from the University of Ohio, Toledo, and a BS in Instrumentation and Control Systems from the University of Mumbai. He is based in KIOXIA America headquarters for San Jose, California. It is my honor to present to you the first keynote of FMS 24, KIOXIA.
Rough start today? Looks like you need high-performance storage for your data center. Make it with KIOXIA. What happened to the music?
Yeah, come on, bro.
Sounds like your laptop needs a performance kick? Make it with KIOXIA.
Keep your back straight. Bend your knees.
Need some help? Improve your game with this. Fast analytics using BICS Flash memory. Make it with KIOXIA.
Have you tried artificial intelligence? Just be sure your AI application has the right storage. Make it with KIOXIA. Upgrade it, create it, analyze it, innovate it. Make it with KIOXIA.
Good morning, everyone. Good morning. It's an honor to be here up on the stage representing KIOXIA. My name is Atsushi Inoue. I'm a VP and Technology Executive of Memory at KIOXIA Corporation. Today, we'd like to share our view of the NAND market details of our BICS Gen 8 and our future migration plan, followed by the introduction of the SSE storage innovation by my colleague, Mr. Neville Ichhaporia. Let me start with this slide, the evolution of the 3D flash memory. Since the introduction of the 3D flash memory, the prevailing paradigm for its technology has always been to shrink the die size by stacking more layers, which is the vertical shrink, and by lateral shrink. But over the past few generations, it has weighted heavily more on stacking layers, which resulted in a CapEx-intensive structure. The graph on the left is the data from the analyst, which shows what I just mentioned. Until the downturn in 2023, the CapEx NAND vendors were spending had an upward trend, and CapEx intensity, which is CapEx over revenue, also showed an upward trend, which is shown in the pink line. The graph on the right is provided from our internal sources, shows that CapEx related to stacking layers and forming memory holes have an upward trend over the BICS Flash generation. So we believe it is fair to say that stacking layers results in higher CapEx intensity, and when this CapEx intensive structure met the worst downturn ever in NAND history, the outcome was devastation of the operating margin for all NAND vendors, including KIOXIA. Here, I would like to talk about the concept of CapEx efficiency. With a fixed set of equipment, in order to increase the gigabyte output from the wafer, the number of layers which correlates to CapEx needs to be increased. This is the vertical shrink. But there is a point where the gigabyte output starts to saturate due to the limitation of the equipment. So in this case, the saturation point, which is circled, is considered to be the most efficient point. In the next generation, when you migrate, in order to further increase the gigabyte output, novel equipment is necessary. In most cases, increases the CapEx significantly. So in this example, the gigabyte output is increased, but it's not proportional to the CapEx increase, which means that this migration really isn't effective. The smaller capacity dies like 512 gigabit and 1 terabit TLC tend to have this issue today. The example on the right is an ideal scenario where the CapEx is effectively utilized to further increase the gigabyte output. As the CapEx related to stacking layers and forming memory hole is increasing over the generation, realizing this ideal scenario is getting much more difficult today. Now let's talk about the lateral shrink. In general, the lateral shrink can be done by relatively smaller amount of CapEx, but boosts the gigabyte output significantly. However, it requires to overcome many different types of engineering challenges, such as architectural change, design changes, process changes, and so on. I will talk about some of the lateral shrink technologies in the later slides. Now that I talked about the concept of the CapEx efficiency, I would like to make one statement. If there's any misconception that achieving higher layer counts is the technology advantage, I would like to say that that's not accurate. The real core of the technology lies in maximizing the gigabyte efficiency, which is finding the right balance between the vertical shrink, the lateral shrink, and CapEx utilization. This approach is crucial in order to deliver more gigabytes to our customers and at the same time ensure sustainability. Talking about the gigabyte efficiency, let's take a look at our BICS Gen 8, which is in mass production today. We migrated from the BICS Gen 5, a CNA technology, to BICS Gen 6, a CUA technology. And after the BICS Gen 6, KIOXIA made a decision, aided by the maturity of the CBA technology, to make a significant improvement in increasing the gigabyte output and efficiency by introducing the BICS Gen 8 without going through another generation of the CUA technology or without adding significant amount of more layers, which was inefficient. We have gained 26% in density from the vertical shrink and 24% from the lateral shrink, including the CBA. So you can see how important the lateral shrink technologies are. With less numbers of layers than the industry's average, which means that it has much better CapEx efficiency, we have achieved the highest gigabit density in the 230-layer generation. So let's look at the lateral shrink technologies that we've implemented in BICS Gen 8. The first one, of course, is the CBA. In BICS Gen 6, there was non-negligible die size overhead in the signal coming from the signal routing area to connect the CMOS and the cell array. And this was minimized in BICS 8 thanks to the face-to-face connection of the CBA technology. Also, from the performance and cell reliability standpoint, in BICS Gen 6, optimal thermal could be applied to the cell array. Optimal thermal could not be applied to the cell array because it would cause degradation to the CMOS underneath. But in BICS 8, since the two wafers, the CMOS and the cell array, are processed independently, optimal thermal could be applied to each wafers, which resulted in better performance and reliability. As one of the other lateral shrink technologies, let me talk about the OPS. The OPS stands for on-pitch select gate and contributes to reducing the area overhead in the wordline layers. Until BICS Gen 6, many rows of memory holes were sacrificed in order to create a physical isolation at the select gate layer to enable the physical pages to be selected individually. This created significant amount of overhead. In BICS Gen 8, we completely eliminated this overhead by creating the separation in between the memory holes, making some of the select gates in a semicircle shape without causing any degradation in the switching characteristic of the select gates. This is a unique technology developed by KIOXIA and our partner Western Digital. Everything combined all together, the BICS Gen 8 1 terabit TLC, which is in mass production today, offers the following: more than 18 gigabit per square millimeters in density, 3.6 gigabps interface speed, 35 microseconds read latency, 200 megabyte per second write performance, and over 1.5 gigabyte per second per watt write power efficiency, while maintaining the most optimal CapEx efficiency. These best-in-class performance were achieved. I like to say that this is the technology leadership, and it's not just about the number of layers. And I hope everyone here agrees to that. As we announced in July, we are also sampling the 2 terabit QLC, which is the largest capacity QLC die available in market today, using the same Gen 8 technology. It offers more than 23 gigabit per square millimeters, which is 2.3 times dense compared to the BICS 5 QLC used in data center applications today. Also, its write power efficiency is more than 70% better than that of BICS 5 QLC. By stacking 16 dies, we can achieve 4 terabyte in a jet extender package, and 128 terabyte SSD can be achieved by placing 32 of those packages onto the PCB. This is a significant leap, and such high-capacity SSDs will be one of the most important building blocks in a data center infrastructure to support the next generation applications. We are working on to stacking more dies, such as 24 and 32, to enable even higher capacity SSDs. Lastly, let me talk about KIOXIA's future migration strategy. We call it the dual-pronged migration strategy. First of all, KIOXIA will leverage our CBA technology and combine it with the existing stacking technology to increase the gigabyte output and address the performance requirements for smaller capacity dies. This way, we can offer the high-performance NAND with the CapEx being minimized. Also, we will continue to develop the cutting-edge technology by utilizing both the most advanced vertical and lateral shrink technologies, just like before. And this will be the Gen 10. CapEx investment will be focused more on products capable of achieving a huge gigabyte output leap, such as large capacity QLC die. KIOXIA will make the most effective use of the CapEx, blend the two migration paths, and contribute in delivering more gigabytes and performance necessary for a wide variety of applications. That's it for the memory. Thank you. And now let me hand the microphone over to Neville, who can share some perspective on SSD storage innovation and its impact at the application level. Good luck.
Thank you, Inoue-san. Good morning, everyone. My name is Neville Ichhaporia, and I'm the Senior Vice President and General Manager of the SSD Business Unit at KIOXIA America. It is a pleasure and an honor to be here with you today. Before I begin, let's recap 3 key takeaways from Inoue-san's presentation, shall we? The first one is optimizing CapEx efficiency is probably a more important consideration driving KIOXIA's future NAND migration strategy than simply maximizing layer count. The second one is KIOXIA will continue to deliver improved capacity density, performance, and gigabyte output as it transitions its BICS Flash roadmap to this new CBA technology foundation. And the third one, and the final one, is KIOXIA will drive a dual-pronged NAND migration strategy that will enable our customers to make the right choice of node for the right application. This strategy at the media level can create opportunities at the storage device level across 4 key vectors: capacity density, storage performance, power efficiency, and innovative features. And each of these vectors can have a transformative impact on today's application landscape, particularly as AI workloads now become an important consideration for future SSD design. So let's take a look at how some of these improvements in flash technology can deliver to the promise of larger, faster, and perhaps more capable, more efficient SSDs in the future. Now, in storage systems, SSD performance directly impacts the speed of data access, the responsiveness of the application, and of course, the overall system efficiency. And in just the past 5 years, the industry has already delivered 2 generations of performance improvements from PCIe 3 to 4 and then from 4 to 5. And today's PCIe 5.0 SSDs, like KIOXIA's dual-port high-performance CM7, are now enabling next-generation applications like artificial intelligence, machine learning, deep learning. And projecting forward, as we move to PCIe 6.0 first, and then we have line of sight to PCIe 7.0 with data rates of 56 gigabytes per second, nearly 4 times as fast as what we can see today. This opens up new application possibilities for data-intensive markets like next-generation compute, automotive, and high-performance compute. And this trend is expected to drive SSD bit growth, strong SSD bit growth, for many years to come. Now, the industry has done a great job of delivering the NAND interface speeds to enable the performance at the application level. And for more than a decade, through the introduction of PCIe 4.0, the legacy trusty 2.5-inch enclosure has served us pretty well. without much need for innovation at the form factor level. But starting with PCIe 5.0, Flash-enabled EDSFF form factors are now being deployed to address some of those concerns associated with elevated performance, like noise and signal integrity and heat dissipation, while still scaling performance and capacity to the levels you see here. And finally, as we move to PCIe 6.0, and the market shifts to those 2 terabit die densities that Inoue-san was talking about, what you're going to see is the increased die parallelism and the increased power budgets now combined to enable extreme capacity, density, and performance scaling, thereby enhancing both access density, which is how quickly you can get data out of the drive, and rack density. Talking about rack density, as AI architectures evolve to feed those data-hungry GPUs, petabytes per rack, or rack density, has emerged as a key operational metric in the new data center. Regardless of the choice of your SSD form factor, whether it's E1.S or E3.S or even U.2, drive capacities are going up, and they're going up considerably. In fact, with a 2 terabit die, you can now scale rack density in excess of 300 petabytes per rack. That's incredible, and it's way up from where we were a couple of years ago. Today's high-capacity SSDs also possess unparalleled TCO advantages from all that consolidation of power and cooling and other savings, which makes them ideal candidates for AI-centric storage. And KIOXIA will introduce its next wave of high-capacity enterprise and data center drives on its BICS Flash Generation 8 portfolio in the future. Now, as these high-cap drives become more and more prevalent, increasing storage density now presents a pretty big and meaningful challenge to the early detection and correction of errors. What happens is these modern storage systems continually read and check and read and check all of this data in a process we call data scrubbing, an operation that ensures that the integrity of the stored data. Now, various implementations exist, but they all involve moving data from these SSDs to compute units through PCIe and memory subsystems and fabric. This is followed by a data integrity check, which involves calculation of a hash or a checksum or RAID parity, and then you get a comparison to the expected value. If everything checks out, which is the desired outcome, then you're done. But what happens here is 100% of all of these computations and data movement is ideally throwaway work, which penalizes our most essential, most critical, most precious resources, which is your network and memory bandwidth. So data scrubbing essentially incurs a consistently occurring overhead penalty that must be paid to ensure data integrity. Now, this problem is compounded by the fact that in today's data centers, exabytes of data pass through your CPU, network, and DRAM. So the data scrubbing penalty gets compounded, it gets amplified, potentially by orders of magnitude. So we ask the question, what if we, the SSD guys, could offload this predictable, repeatable, fixed function data scrubbing task to the SSD? Well, KIOXIA plans to equip future SSDs with embedded logic like controller memory buffers and compute engines and DMA controllers to facilitate offloading these multiple functions like RAID offload and data scrubbing and potentially many more. So the best part of this whole activity is these resources exist today, and we're just making them available to the host through a standards-based process and approach. Take a look at this data. The savings are pretty incredible. Our simulations show that systems can scrub data with up to a 99% reduction in host resource utilization. So again, if you're interested and if you want to learn more, please stop by our booth or attend our panel session. Now, another innovation that KIOXIA is looking into is memory expansion capability using a low latency XL flash memory. The data shown here compares GPU graph processing runtime when graph data is placed in CXL memory versus host DRAM. And our investigations have shown that a modest amount of DRAM cache in conjunction with XL flash memory can yield average latencies less than 1.6 microseconds for a 256-byte random access. So this solution has the potential to deliver DRAM-like application performance for various workloads using relatively cost-effective XL flash memory. We are presently building a POC and are eager to work with our partners and customers to explore the benefits of memory expansion. So if you're interested, please stop by our booth and check it out. Well, let's talk a little bit about AI. In today's enterprise AI server environment, from data ingestion to AI training to AI inference and grounding, SSDs now play a critical role in data storage. So given its capacity density and cost advantages relative to DRAM, how can SSDs play an even bigger role in the future of GPU-connected AI architectures? Well, let's ask someone who knows a thing or two about storage technology as it directly relates to AI and GPUs. Joining me here today is Rob Davis, Vice President of Storage Technology at NVIDIA. Come on out, Rob. Rob, thanks so much for joining us today. If you could just spend a few moments talking about some of the challenges you see with GPU storage and opportunities for SSDs and memory tiering, that'd be great.
Be happy to. Okay. Hello, everybody. First of all, I want to thank KIOXIA for inviting me to be a part of their keynote here at FMS. I almost said Flash Memory Summit. It's stuck in my head from years and years. So, how many of you have teenage sons at home? The reason I'm asking is because GPUs are a lot like teenage boys. They're always hungry. Except instead of being hungry for whatever's in your refrigerator, GPUs are hungry for data. As the chart here on the left shows, a CPU's data set is typically measured in gigabytes, but a GPU's data set is measured in terabytes or even gigabytes. And as you can see, the curve is up and to the right, so it's not going to get any better. The way to think about this, or why this is because we all know in a CPU, there's tens of cores. But in a GPU, there's tens of thousands of cores. So to go back to our food analogy, think about feeding a family versus feeding all the people at that football stadium across the street on game day. A big, big difference. So it's great, all the things Neville was telling us about how they're improving the performance of the SSDs, because we're going to need it. And this provides a big challenge. This mass amount of data creates a big challenge for the I/O cycle, the storage I/O cycle of a GPU. If you look at the chart on the right, you see that in a CPU that has a 25 or maybe even 10 gigabit interface, loading a gigabyte of data is not an issue to keep that CPU from having to wait for the data to be loaded. But when you look at a GPU moving in terabytes of data, that 25 gig does not get it there in time to keep that GPU busy. And unlike the teenage boy who complains to his mom about nothing in the refrigerator, the GPU just sits and idles. And it's expensive, so you don't want it sitting and idling. Now, the easy fix is to increase the I/O performance with 200, or we have 400 now, gigabit Ethernet or InfiniBand if you want the ultimate performance. But there's also the storage software stack, and that's where a technology called GPU Direct Storage comes into play. And GPU Direct Storage is part of CUDA, which is the programming framework for GPUs, at least the ones from NVIDIA. And what it does is bypass the host CPU in the GPU server and move the data directly from local or remote storage, remote across the network, of course, directly into GPU memory. And this problem isn't going to get easier, either for training or inferencing, the two main GPU applications. So you can see on the chart on the left that the number of parameters which go into a large language model, which 5 or more years ago was measured in hundreds of thousands, is over 1 trillion today. And that curve is, again, up and to the right. And then we look at inferencing, and there's new innovations happening in inferencing all the time. One of them that's kind of popular now is called Retrieval Augmented Generation, or RAG, R-A-G. We have a lot of acronyms in our industry, but here it's good to have an acronym, because who wants to remember that name? And what happens with RAG is that it actually generates more storage. So it's good to be in the storage industry. And it requires low latency. And the latency is important because in the RAG applications, and what RAG does, I should have told you that before, what RAG does is it basically allows you to use large language models that were trained maybe months or years ago in time-sensitive applications. So for example, if you have a retrieval system, or, you're doing something like a call-in system where you have to have up-to-date data on maybe fixing, TV or something like that. The data has to be updated from long ago in order to be relevant today. Or finance, for example, where it has to be in nanoseconds or at least microseconds. And so the latency is important because that user, which also can be another computer, so that's super important. So what are we doing to try to keep ahead of these curves? Well, first of all, with local storage, a lot of applications for AI actually move the data into the SSDs, the local SSDs, and work off of them. What we're doing is GPU Direct Storage, for example, works there. And we'll talk about upcoming areas called GPU Initiated Storage, where that will improve as well. And then if the data set won't fit all into the local SSDs, we do network storage with our network partners. And we use 200 or 400 gigabit Ethernet or InfiniBand, and we like to use our DPUs, our Bluefield DPUs, to offload and accelerate and secure the data path, and that's also where we're going to be doing a lot of innovation. So if we look at GPU Direct Storage that I talked about earlier, you can see the data path without GPU Direct Storage is in dotted lines, so the data comes out of the storage, goes through the CPU, into the CPU memory, back out of the CPU memory, and back to the GPU. So there's a store and forward with a lot of software. Whereas GPU Direct Storage goes directly from the memory of the local or remote storage into the GPU memory. With GPU Initiated Storage, we actually remove completely the control path from the CPU and put it into the GPU. So now think about all those people in that stadium, drinking coffee. The load on those local CPUs and the remote storage is going to skyrocket. So higher performance needed there. We're also increasing the performance of the network to 800 gig, and we're looking at how to accelerate object storage. So most of the storage, or much of the storage today, isn't in file and block, it's stored in object storage. So we're looking at ways to improve the storage software stack to accelerate object storage as well. And then lastly, we have a new technology that I'm sure you've heard about called Spectrum-X. And what Spectrum-X does is make Ethernet as close as possible to InfiniBand performance. And it does this without changing Ethernet. So you can run your regular Ethernet traffic on it at the same time. And you can see the performance. Now, all the testing we've done, and the focus today is on clustering. So currently, one of the main uses of InfiniBand is clustering together the GPU servers so that they can share information, or because the problem they're working on is split up between all of those different GPU servers. And that's where the focus is today. And you can see that running a regular application, a regular AI application, we can reduce, using Spectrum-X, the latency by more than 4%. And you can see how tight that latency becomes too. Instead of a lot of tail latency, which you see in the blue, the latency is very tight, and that improves the efficiency and again, keeps those GPUs running smoothly. Now, one thing to keep in mind is that this is all done for clustering, but we're now starting to look at it for storage, the storage data path as well, because RDMA is RDMA, right? So an interesting thing about the GPU-initiated storage is now we can add the SSDs to the GPU, to the SSD memory tier. We can add SSDs to the GPU memory tier, because using GPU-initiated storage, we can access those SSDs directly from the GPU, controlled by the GPU. And again, this is going to create a tremendous load on the I/O of the local SSDs and the remote storage systems. And if you want to hear more about that, there's actually a talk by one of my colleagues at 8 o'clock Thursday morning just on that subject. The last thing I want to talk about is go back onto RAG. Now, this is a very complicated system diagram, and I don't have time to actually go through it today, but remember that RAG is increasing the amount of storage needed, so good for the storage industry on inferencing, but also is very latency dependent. And one of the areas where this latency needs to be addressed is in what's called the vector database, which is an important component. And what I'm going to do now is turn it back over to Neville, who is going to talk about how they're working with the SSDs to try and improve that area. Thanks very much for your time.
Thank you, Rob. Appreciate it.
My pleasure.
Thank you to NVIDIA. You guys are fantastic partners. Much
as well as
appreciated.
you are.
Thanks for stopping
Thank
by. Okay, so as Rob just explained, RAG increases the need for storage even further. Let me just double click into this with a two-step simple process to illustrate exactly how. So the process of vectorizing this proprietary data creates these embeddings for RAG solutions that multiplies the size of the data. And these memory-based algorithms like HNSW actually limit the amount of data that can be properly utilized by these systems. So building on the foundation of Microsoft's DiskANN vector database work, it is now possible to build even larger vector databases that use less memory by moving these to SSDs instead. The bottom line here is now we can scale out this external vector data at a relatively lower cost and then retrieve this data quickly and efficiently using SSD optimized ANN search. So this has the potential for lowering the cost of deploying an AI solution. Now take a look at this data that perhaps underpins the assertion I just made. The graph on the left shows that the DRAM footprint for vector databases grows astronomically with the number of vectors or the RAG database size. And this compounds as the number of dimensions for these vectors grows. Now let's compare this with DiskANN's results. As you can see, the memory requirements are substantially reduced. But what is truly surprising here is the graph on the right. Our testing shows that as vector databases scale, you can reach a point where an optimized SSD-based ANN search actually outperforms a traditional DRAM-based search. Now let's go one step further. ISAC is a KIOXIA project to transition from mostly in storage, like DiskKNN, to all in storage vector databases. And ISAC research builds upon DiskKNN's algorithms through further optimizations for SSDs. And preliminary results show virtually no DRAM required while enabling practically unlimited scaling. And at the same time, we see, if you look at the graph on your right, only a modest penalty relative to DiskKNN, while still being substantially faster than DRAM-based HNSW solutions at scale. So these are pretty impressive early results with some profound implications. And so again, if you want to learn more, please visit our booth and learn more about what SSDs can do for your AI solutions. And that brings me to the end of the presentation. Thank you all. Please stop by our booth, check out our demos, as well as our speaker sessions. Thank you.